Okay, back. Okay, back. Okay, back. Okay, back. Okay, back. Hold on, chat. Dude, shut the F up and put that on.
Everything is made of atoms. Yes, even you. Atoms consist.
I bet. Hold on. General chemistry explained in 19 minutes. Yo, tell your teacher. Tell him, please. Please, give me 19 minutes. Give me 19 minutes. Tell him to just give me 19 minutes.
Of a core and some electrons.
Yeah, let's
the
go.
core is made of protons and neutrons, and depending on the number of protons, you get different elements. Water is made of hydrogen and oxygen. This is some sodium. I wonder what happens when you...
Explosion.
Whoopsie.
Explain in a couple of minutes. Let's
This
go!
is not what atoms actually look like. They look more like this, but we'll get to that later. For now, just think of atoms as having multiple electron shells. The electrons...
Yo, that's actually crazy. Like, I'm really realizing, like, this stuff be just roaming around in the air. And we can't see it. But, like, it's there. It's in front of you, and it's, like, in front of me. It's everywhere. This weird-looking thing. But we can't see it because it's, like, so small and, like, I don't know. Some weird energy stuff.
Valence electrons. Most of chemistry is really just the behavior of these electrons. Every element is
electrons.
listed in the periodic table. All elements in the same column behavior of these electrons. Every element is
the
listed
periodic
in the periodic
table is like one of the worst things ever made. Genuinely one of the worst things ever made. It's so complicated. Like it literally took me when I first learned about the periodic table back in like 9th grade, I think, 10th grade. Bro, like I spent like a good like 24 hours just looking at it, trying to understand what the hell was going on. I think I got it though. One side is metals. I think this side is metals, right? The other side is non-metals, I think. Solids would be, I think, this color. Cause like they're all separated by different types, right? Solid, liquid, and gas. I don't know which one's liquid. Maybe the red. Gases, helium, hydrogen. Okay, I'm actually not trying to embarrass myself because I don't know. Yo, I don't know anything about periodic table. I'm sorry.
Table. All elements in the same column or group have the same number of valence electrons. For the main groups, the number of valence electrons is just the group number from 1 to 8. Except for helium. It's too small to have 8 electrons. It can only have 2, but still, it acts like a noble gas, so it's just...
Told you. Did I not say helium's a gas?
Kind of grouped in with those. Luckily, the transition metals also follow
and put
a nice
that
pattern.
Game on.
That was a lie. It's kind of a mess, but that's not so important for now. So
I just read your chat twice.
Elements with the same number of valence electrons tend to show similar behavior in chemical reactions. For example, the first group without hydrogen is called the alkali metals. Here's some things they have in common.
Alkali metals. Okay. Okay. Chat, this is the alkaline metals. Lithium, sodium, potassium, rubidium, caesium, francium. Yo, what the hell is it? Yo, mind you, a grown man named every single one of these things. Maybe not the same person, but like over time. Just group of people just started naming all this stuff. Why the hell would you name something like potassium or caesium? Like, that's so like lame. What the hell is that even? What does that even mean? And why do they all have at the end? But anyways, these are the alkaline metals. So these are all metals. We gotta know that. The red ones are the metals.
Alkali metals. Here's some things they have in common. They have one valence electron.
One valence electron.
They're
Shiny.
Kind of
soft.
And they do this sometimes. All elements in the same row or period have the same number of shells. This number increases from top to bottom. Also, the mass gets bigger from left to right as each element gains a proton, an electron, and some neutrons. Depending on the number of neutrons...
Yo, protons and electrons really be roaming around. We just can't see them. Electrons, atoms, all that.
You get different isotopes of the same element,
That's
most
crazy.
of which are pretty unstable and fall apart, releasing ionizing radiation. Fun fact, that stuff will kill you. If an atom has the same amount of electrons as protons, it has no charge. If it has more, it has a negative charge, and if it has less, it has a positive charge. Charged atoms are called ions. Negative ions are anions and
Okay. So the ones with the positive are ions. The ones with the negatives are anions. Got it.
ions are cations. The periodic table is also pretty much a
Cations.
dictionary, as every cell tells you the name and symbol of an element, the number of
Okay. So the numbers actually have meanings. The top one's the number of protons. The number or protons? Yo, this dude messed up with his freaking video. Dude said number or protons. He meant to say number of protons. This goofball, bro. And in the bottom, what did he say? What's the bottom?
protons in the corpuscle is also pretty much a dictionary, as every cell tells you the name and symbol of an
The name, obviously. The symbol, sure.
element, the number of protons in the
Okay.
core, which is also the total number of electrons, and the atomic mass, which is the
The atomic mass. Chad, do y'all know your atomic mass? Do you know your mass of atomic is? The atomic mass equals neutrons plus protons. Measured in U. We're measuring. I don't even want to say it anymore. Measuring neutrons plus protons. Mass in U.
mass of neutrons and protons combined. The periodic table is roughly divided into 3 categories. Left of this line are the metals. Right of it are the non-metals, which are mostly gases.
Yo, I was right. I was right.
Left of the mass of
Hold
neutrons and
on. I
protons
was right.
combined. The periodic table is roughly divided
I said the left side was metals. I said like a good amount was on the left side. I didn't say anything was on the right. And on the right, there's hella gases and stuff like that.
into 3 categories. Left of this line are the metals.
I told you. I said not hydrogen though, because hydrogen's a gas. But I thought I was an idiot for saying that. But I'm not. I'm right. I didn't know all of them were metals, but I knew majority of them. Iron, cobalt, nickel, copper, silver, aluminum, Tennessee, copper, nicium, hacium, gold. Oh, I didn't know we had gold on the periodic table. Titanium, radium, magnesium, calcium's a metal. I didn't know that either. Wait, hold on, chat. I'm getting a call. Hello? Alright.
Right of it are the non.
Alright, now the non-metals. I knew that. Obviously, carbon. I knew helium. Oxygen, obviously. Chlorine, yeah. Phosphorus. Iodine, bromine. I know all those. Is bromine a gas or a liquid? I seen a clip of like bromine being dumped into like a glass, like those glass science jars that they use for like experiments, but it was like a liquid at that time. But I don't know if like they did something to it to do that.
Metals, which are mostly gases, and the line is called
Mostly
the
gases.
semimetals.
What I said. I told you I know this. I do chemistry for a living. I wake up in the morning and I just think about chemistry. Like I know this. Semi-metals. Boron, silicon, germanium, arsenic, antimony, tellurium, astatine, astatine, kryptonite. Yo, we have kryptonite as on the periodic table. Dude, what? We could make it? I thought kryptonite was like on another planet. Bro, Superman ever comes to Earth?
Which have properties that fall somewhere.
We got kryptonite.
2 or
Like,
more atoms
he's
bonded
done.
together
If he
form
ever
a
tries to
molecule.
mess
If you
around.
have at least 2 different elements, you get a compound. Oh yeah, this is probably a good time to mention that compounds often behave completely differently than the elements they're made of. Like, put together an explosive metal and a toxic gas, and you get, of course, an even more
explosion.
table salt. You get table salt. There's many ways to write
That's
molecules.
how they
for
make
example,
table
the
salt?
molecular formula, where you just count the number of each atom in a molecule and write them as a subscript
H2O
number next
water?
to the element symbol. But that
That
has
makes
some
water?
problems. Look at these 2 molecules. They have the same molecular formula, but obviously they're not the same. They're isomers. Showing this
They're
difference is probably
isomers.
kind of important. It's the only thing that separates graphite from diamonds because they're both just fancy versions of carbon, and I don't think
Fancy
anyone's going to
versions of
go,
carbon.
yes, this dusty black blob is indeed very expensive. One way to show the structure of an atom is the Lewis dot structure, which represents the valence electrons.
Holy
and
crap.
One way to show the structure of an atom is the
Lewis dot structures. I'm not gonna lie. I'm guessing the dude who made this, his name is Lewis. Lewis, slow the hell down. Slow the hell down. Like, what kind of symbols is this? You just put an S in the middle. O's everywhere, a whole bunch of dots. Then on the right, we got the same thing, but with lines. Why are you doing this? Yo, Lewis, slow down, bro. Yo, you could make chemistry a lot more understandable if you actually make it funner. And you do it less complicated. Why did you have to explain chemistry through O's and S's, through dots and lines? Should have done something better. I don't know what, but like, you could do it better. How do you even discover like atoms and chemistry and all that? I feel like that's a pretty like logical question to ask. How did they even think of this? How did they even think of an atom like, oh, there's atoms all around us? How did they even find that out? Genuinely. What if they just lying to us at this point?
dot structure, which
They're just
represents the
adding
valence
stuff, so we have to
electrons
do
and bonds
something.
as dots and
So we have to do
lines.
something
This
at
is
school.
also going to help us understand why atoms bond in the first place. You see, everything in the universe wants to get to a state of lower energy. That's why a ball on a hill will roll down by itself, because that decreases its potential energy. This trend
Less
also applies
potential
to
energy.
atoms. The state of lowest potential energy is having a full outer shell of electrons, which is most often 8, or in the case of hydrogen and helium, 2. If you think back to the periodic table, you'll see that all noble gases already have a full outer shell, which is why they don't really want to react with anything. If two atoms don't have a full outer shell, but can achieve one by sharing electrons, they will naturally do so. The same way a ball will go downhill.
I get it now. Oh, okay, Lewis, I'm not gonna lie. Nah, I was just playing, bro. You cooked. You're cooking. I know what you mean. I see what you mean. Okay, so since there's dots around it, like this is the compound. As an example, F. I'm guessing it's fluorine. And since it's missing a dot, and I don't know what the dots are. Are they atoms or something like that? Electrons? I don't know. But since it's missing one, the dot, they're able to go together and connect. Like connect together. Because they have what they're missing, like the missing piece. I get it now.
The full
Lewis is
outer
actually
shell can
cooking.
achieve one by
Never
sharing
mind, Lewis is
electrons, they will
cooking.
naturally do so. The same way a ball will go downhill, as their combined
Okay.
energy would be lower than if they were
Look,
separate.
now they're
The sharing
combined
of
now.
electrons is called a covalent bond. These bonds
Okay,
are
a
also caused by the
covalent
positively
bond.
charged nucleus of an atom tugging on electrons of another atom. The
Okay.
strength of this pull is called electronegativity. In the periodic table, the electronegativity increases from bottom left to the top
Magnets.
right. Therefore, fluorine has the strongest pull. It's just
Okay.
unbelievably desperate for an electron. If the difference in electronegativity is bigger than about 1.7, you get an ionic bond. A
An
good example
ionic
is sodium
bond.
chloride. Chlorine would do anything for an electron, while sodium has one too many and just kind of wants to get rid of it anyway. Perfect, they both say, forming an ionic bond, where
Wait. Why does he only have one dot?
sodium loses an electron and turns into a cation and
Okay, so if you don't have any an electron. If you don't have any electrons, you turn into a cation. I understand it now. No, I look
chlorine
get it.
gains an electron and turns into an anion. That seems pretty important.
And then I'm guessing the ones with all the electrons are called the anion. So the compounds without electrons are cations. The ones with electrons are cations. Yo, chat.
You might want to remember.
Dude, I could be a
The most
scientist.
common place you see ionic bonds is in salt.
Yo, when am I
Yes,
gonna
also
discover,
total
like,
but
another
more
atom?
generally when metals and
When am I
non-metals
gonna
bond, you
discover
get
another-
salt, which is just a grid
another
of ions.
science?
Speaking of metals,
Another
a pure
science
metal
fact.
forms metallic bonds. You can imagine this as a huge grid of positively charged nuclei which are surrounded by freely moving electrons. You see,
Okay.
in a metal grid, the valence electrons are kind of promiscuous, whereas the nerds call it
Promiscuous.
delocalized. They can
That's
move
a good
freely
word.
in a
I like
giant
that word,
playground of nuclei
promiscuous.
instead of being loyal to just one. This kind of bond is responsible for the properties of metals, like conducting
Okay.
electricity and heat, and also being malleable, as in being kind of bendy. Like, you can hammer on this stuff until it's the most deformed, unelegant,
Oh, what the
and
hell?
ugly-looking piece of material ever known, and it will just limp along as if nothing ever happened. If the difference in electronegativity is lower than about 0.5, the electrons are shared pretty equally and you get a nonpolar covalent bond.
Okay.
If it's bigger than 0.5 but smaller than around 1.7, one of the elements is pulling on the electrons.
1.7 what? Like what where did that number come from? And how do you even like calculate the number?
To skew the electrons a bit, making it a polar covalent bond. An
Polar
example is water.
covalent bond.
Oxygen has a very high electronegativity compared to hydrogen. As a result, it pulls the electrons of hydrogen so hard that they kind of belong to oxygen, giving it a partial negative charge and leaving hydrogen with a partial positive charge. The presence of two poles with opposite charge is called an electric dipole. All permanent dipole molecules can interact with each other, and really with anything that has a charge. As a result, the molecules will tug on each other and arrange themselves in a way that oppositely charged ends are next to each other. The forces acting between them...
Bro, what is that? I've never seen that letter a day in my life. Like, I've never seen this in the alphabet. Where the hell did this guy get this from?
Called intermolecular forces, or IMFs.
Someone just lied to him and told him it's a
hydrogen
Q.
bonds, where hydrogen bonds to something very electronegative, like fluorine, oxygen, or nitrogen, creating strong dipoles that tug on each other. But even if molecules are not polar at all, there can be electrostatic forces acting between them. How? Electrons move around inside the atoms, and by pure chance, they can end up on one side of the atom, creating a momentary dipole, which influences other particles
electrons
next to
are
it
so
to become
weird.
a dipole as well.
I want to see like an electron.
Time, as the electrons keep
like
moving and the dipole disappears.
This
is called the van der Waals forces. The polarity of water also explains why it's one of the most versatile solvents to exist.
I mean a
It
microscope.
can pull apart molecules by tugging on charges, and it keeps them apart by surrounding a particle with its oppositely charged end. Water cannot dissolve nonpolar molecules, though. It's the reason why water and oil don't mix, since fat molecules are nonpolar while water...
That's crazy. Like, they're not separating anything. There's not like a glass right in between these two. It's this literally just water and oil. But the fact is, because of the science behind it and the molecules and the whole bunch of guacamole, it won't mix. So they just layer on top of each other. That's actually weird. If it's like a solid item or a solid object, then I won't be like shocked, because that's just normal. Like, you feel me? I could put my hand on top of my other hand and it won't fuse together. But the fact is that they're both liquids and they're not even mixing at all while being on top of each other like that. That's so that's so weird.
Water is polar. Just remember the ancient saying, similia similibus solventur.
Similia similibus solventur. Right, I did that first try. Light
Or
word.
in a language that's actually spoken, similar things will dissolve similar things. Fun fact, soap works because the molecules that it's made from, which are called surfactants, have a polar head and a nonpolar tail. This way, when in water, they can surround, for example, nonpolar fat molecules and form micelles, which, along with the water, transport the dirt particles away.
Oh, so that's how soap works. Hold on, chat. Let me make this so y'all can understand. When you're washing your hands, because of the soap and the nonsense inside of it, it attaches on to the dirt and the fat. So then when you put the water on, the water just drags the micelles.
Polar fat molecules and form
Hold on. Like this, it just grabs onto it. This is the soap. And then with the water, when you put the water, it drags the micelle away.
Cells, which along with the water, transport the dirt particles away.
Yo, I can do this. I can make this video.
Forces ranked by strength. Ionic bonds, covalent bonds, metallic bonds, hydrogen bonds, and van der Waals forces. There are three main states of matter: solid, liquid, and gas. Solids are tightly packed in fixed structures.
Oh, I know this one too. When it's solid, all the... I don't want to be dumb and say, I don't know if it's electrons or something in it, but the particles, they stand very firm together and they barely move. Then with liquids, they have a bit more space, so they're moving around a little bit more space. They get to move a little. And then with gases, gas is just, it has so much space that they're just going crazy, hitting walls and stuff like that. Dude, I know that. I know this already.
Where the particles can
I learned this back in like
unless,
8th grade.
You smash them. In liquids, the particles can move freely but are still confined to a fixed volume,
You
as
see
the
it?
forces between them are still strong enough to keep them together. And the particles in gases have enough energy to just do whatever they want and fill up all the volume you give them.
And just go
Knowing
crazy.
this, we can find two important words. Temperature is the average kinetic energy of particles in a system, or how much and how fast they move, and
Kinetic
entropy is the
energy.
amount of disorder.
Isn't kinetic
Substances
energy
tend
in
to be solid at
physics,
low temperature
not
and
chemistry?
or high pressure, which is a state of low entropy, as they're neatly organized
Low
and don't move that
entropy.
much. And gas at high temperature
I remember
and
that
low
word.
pressure, where they move around like crazy, so it's a state of high entropy. Strong
High
bonds,
entropy.
like ionic bonds, lead to high melting points, as they take a lot of energy and therefore a high temperature to break apart. That's why most salts are solid at room temperature, whereas water, which is only being held together by hydrogen bonds, is a liquid. Well, actually, there's another state called plasma, which is ionized gas and can exist at very high temperatures, such as in stars, or very high electric potential. The latter is used for neon
Interesting.
lights. Gas is ionized in a tube with a very high voltage. Collisions of the ions with other particles makes their electrons move to a higher energy state. Once they fall back down,
N2,
the difference
N1
in
is low energy?
released as light. The color of the light depends on the element that's used
Color
in
of
the tube,
light.
as each element has different but fixed energy levels, and the difference between
Yo, this
those
guy's
determines the energy and
speedrunning
therefore the
this.
frequency
Holy
of the released
crap.
light, which is what changes the color. All possible
Wavelength. Wait, each wavelength has different colors? Intensity A or B?
frequencies that an element
What?
can emit are called the emission spectrum. All matter can be divided
The
into two
emission
categories.
spectrum.
Pure substances, which can consist of one element or one compound, and mixtures. Mixtures consist of at least two pure substances and can be homogeneous or heterogeneous. Homogeneous
Yeah, homogeneous is when they do mix. Heterogeneous is when they don't mix. I know that already. Dude, I know
means
all
the
I know
substances will mix
all
evenly
about
and
this.
the mixture looks the same everywhere, like salt and water, which is a solution. Heterogeneous mixtures look different depending on where you look. They have distinct regions made of separate substances. One example is sand and water, which is called a suspension. Okay, well, what
Interesting.
about milk? That looks the same everywhere, so it must be homogeneous.
Yeah.
No, milk is something we call a colloid, or more precisely, an
No?
emulsion. The difference between salt water and milk is that the solute doesn't fully dissolve in the solvent, meaning there are bigger particles. The
Hold on,
difference
chat.
between salt water and milk is that the solute doesn't fully.
So you're telling me there's this crap in my milk? So when I'm drinking milk, it's not actually dissolved stuff or whatever? We got tiny bubbles of fat? I'm not gonna lie, I might be done with drinking milk after this video.
dissolve in the solvent, meaning there are bigger
kinda
particles than in
like-
a solution.
I don't know if
but
that's
smaller
nasty,
particles than
like
in
nasty or
suspension.
not, but it's
This
just kind of
allows the
weird, like a
particles
weird
to stay
thought.
evenly distributed, but not fully
I don't like that
dissolved,
thought.
placing them somewhere between solutions and suspensions. Hey, remember sodium
Weird.
and water? What's going on there? Explosions are really just chemical reactions that release a lot of energy in a very short amount of time. Also, they expand, like, a lot. There's a couple types of chemical reactions: synthesis, decomposition, signal replacement, and double replacement. Here's an
Holy
example
frick.
for each one. They all happen mainly for one reason: to decrease energy and get to a more stable state. Chemical reactions
Yeah,
happen in
the
certain
goal is to
ratios.
do
For
less
example,
work.
to produce water molecules, you need twice the amount of hydrogen compared to
Goal is
oxygen.
less work.
This is called stoichiometry. These ratios are based on the conservation of mass, which says that mass cannot be created or destroyed, only converted. Practically, when dealing with reaction equations, you have to make sure that
So
there's
everything
the
you
same amount
make
of atoms on
are-
each side of the
no.
equation, and if
Nothing can be created, only replaced or transferred. It can't be created or destroyed. Any form of matter. So even if you burn something to ashes, like it didn't disappear, it just burned to ash, and then the ash will form into something
not,
else,
balance it out element
and
by
the matter
element.
would just be
As a
something
rule of
else.
thumb, you should balance out the metals first, then the nonmetals, and then hydrogen and oxygen. At
Oh yeah, I
the
learned
end.
this in
But
class,
it's
how
really
to
just trial and
balance
error until everything is balanced.
balance the
Okay, but if you
equations
wanted
out
to
so
make
everything
this
can
reaction
balance
happen in a
each
lab,
other out
how
and
would
be
we know
good.
that we have exactly twice the amount of hydrogen
It's not even
compared
hard.
to oxygen? You can't just
It's
take
actually
10
not hard.
grams of this and mix it with 20 grams of that, because the atoms don't weigh the same, so 10 grams of both contain a different amount of particles.
What
to
the
do?
hell?
Just look up the atomic mass of the reactants and take that amount
Oxygen.
in grams. You'll get exactly this amount of particles. That is 1 mole, which is just an
1
amount
mole.
of something, kind of like a dozen. In other words, we can interpret the reaction as 2 moles of this react with 1 mole of that, which we can easily measure. It's important to
Oh,
differentiate
mole? I don't
between
understand the
physical
mole
and
part.
chemical changes.
Yo, I don't understand what they mean about mole. Like, are they talking about like actual moles, like the animal, or like what do they mean by mole? What's a mole?
As reactions
I don't
only
get
take
it.
place in the latter.
That I
Physical change
don't
happens
understand
when the
at all in
appearance
chemistry.
changes,
Like,
but
what
the
do you mean
substance does
mole?
not. For example,
And
hammering metal.
if it's
A
something
chemical
else,
change
like
happens when the substances
just
themselves change.
name
and
it
this is often
something
accompanied
else.
by bubbles,
Like, that's already
a
an
funky
animal's
smell,
name. Like,
or you guessed it,
leave it alone.
explosions. All chemical
Name it something
reactions
else.
need activation energy to take place. Wood won't just spontaneously react with oxygen
Hey,
and
cutie.
start burning, or else, the planet would be on fire, but if you give it enough energy, it will. Catalysts reduce the activation energy needed for a reaction, which makes it happen easier and faster. And as a neat bonus, they don't even get used up during the reaction, so you can just reuse them. Because
Shout out
chemical
Mark
reactions
Robert,
are
bro.
changes in energy,
Mark
it's quite
Robert is probably
useful to
like the
keep
best
track of.
scientist of all
Enthalpy
time.
is simply put the internal energy.
Genuinely
or heat
like
content of
top
a
3
system.
scientists of
If
all
the total
time.
enthalpy of a reaction is lower at the end than at the beginning, heat was given off to the surroundings, which is an exothermic reaction. If it's the other way.
Oh, I know that. Exothermic gives off heat and it stays cold. Endothermic receives heat and stays hot.
Around, a reaction is endothermic. It's easy to see how exothermic reactions can be spontaneous. It's kind
Told
of like
y'all,
a ball
chat.
on a hill. It will only start rolling if you push it a
Chat,
little
told
bit, but
y'all.
then it will keep rolling on its own. Just like wood keeps burning on its own. But in endothermic reactions, you have to keep putting in energy, like pushing a ball uphill. That doesn't just spontaneously happen, right? Well,
Maybe.
yes, actually it does. To get the whole picture, we have to look at Gibbs free energy, which looks at the change of enthalpy, but also the entropy of a system, which is dependent on temperature. If this whole thing is less than 0, the reaction is exergonic, or spontaneous, because free energy was released.
Exergonic.
If it's bigger than 0, it's endergonic, or not spontaneous, because free
Endergonic.
energy was needed and absorbed. Here's where temperature
That's a
and
weird
entropy
word.
come into play. Even if delta H is positive, so the reaction is
Delta H.
endothermic, if the change in entropy is big enough, it can offset this and make the total free energy negative, which means the reaction is spontaneous. But this is strongly
Spontaneous.
dependent on the temperature. For example, melting an ice cube is endothermic because it absorbs heat, but also it increases the entropy a lot, as neatly organized ice turns into water, which is just kind of a mess. So this can happen spontaneously, but only if the temperature is above 0. If it's below 0, the water will
Oh my
spontaneously
gosh,
freeze,
holy
which is
crap.
exothermic. If it's exactly 0, then no reaction
Holy
will take place
frick.
spontaneously. In other words, if delta G is 0,
I don't know
we're
how
at
this dude
equilibrium.
just made this video.
Chemical equilibriums exist when reversible reactions take place at the same speed in both directions, which means that even if reactions are taking place, the concentrations of both sides stay the same. And to someone watching
I'm
from
like-
the outside,
I'm
nothing
getting
seems to be happening.
overstimulated with
We
just
often find
watching
chemical
this.
equilibriums in phase changes, but also acid-base chemistry.
Holy
According to
frick.
Brent Lowry, an acid is a molecule that donates protons,
hell
while
are these
bases
guys?
accept protons. A proton in this case is just a hydrogen ion. So, with this definition, a molecule with at least one hydrogen that it can throw away can be an acid, and anything that can pick it up can be a base. This also means that once they
Interesting.
react, they turn into the conjugate opposite, as an acid that gave away a proton can now accept one
Oh
back,
yeah, I know
which is
about
what bases
acids and
do.
bases.
A
That's
molecule
easy.
that can act as both an acid and
A lot of
base is
fruits are
amphoteric.
acids.
For example,
Chat, if y'all didn't know, a lot of fruits are acids. Oranges, lemon, strawberry, bananas. What else is in it? What else has acids in it? Limes. Like a lot of fruits are acidic. And a lot of times, before they drop the foods out, before they drop like the fruits out to the market and stuff like that, they'll get analysts that would check the acidity of the fruits through pH scales. And if it's lower than 7, it's acidic. If it's 7, then it's neutral. It's between acid and base. And if it's higher than 7, it's a base. But anything lower than that, they'll check and make sure if it's at the good acid level. You feel me? If it's at a level 1 acid, like that's how you know, like it's acidic as hell. I don't know what the average is for most fruits, but I think like they strive to get around like 5 or 6, 4 maybe. I don't know.
water. A strong acid will dissociate almost completely into its ionic form, giving off a lot of protons to the water and therefore creating lots of hydronium ions. A weak acid just won't dissociate nearly as much, giving us a lower concentration of hydronium ions. So, to measure the strength of an acid, we can measure the concentration of hydronium ions. This is called the pH. Mathematically, it's defined as the negative log of the hydronium concentration.
Oh yeah, and then that's how they do. They do the math. They do negative log, and then they do some stupid number, and that's how they find out the pH.
Means one step on the scale is a
Yo,
10 times
chat, I
change,
know
and
all
also,
about
since it's
this
a
already,
negative
like,
log, the higher the
I did
concentration,
chemistry
lower the
like
pH.
back in the
For
day,
example,
man.
pure water is in a chemical
Back in the day,
equilibrium.
like,
there's exactly
in
one
prime
hydronium
time,
ion for every 10 million
I do
water
chemistry every
molecules.
single day.
In other words, the
I do it with a
concentration
smile
of
on my
hydronium
face.
is 1 over 10 million, or 1 times 10 to the negative 7.
1 times
Taking
10 to the
negative log of this
negative to the
gives us
power
a
negative
pH
7.
of 7, which is considered neutral. Anything lower than 7 is acidic, and anything above is basic. Unlike
Told
you,
y'all,
you
chat.
can do the same thing with hydroxide ions
Told
and you'll
y'all,
get
chat.
the pOH, which keeps track of basicity. Fun fact, the pH and pOH will always add up to 14 because they counteract each other.
14.
So by knowing one, you know both. Now, if you have a strong base and a strong acid and you pour them together, no, they will not explode. They will neutralize by forming water along with the salt, which is neutral. For example, hydrochloride and sodium hydroxide will form water and table salt. Oh yeah, speaking of table salt, remember how it consists of ionic bonds because sodium transfers an electron to chlorine? Well, that is called a reduction-oxidation reaction, or redox. If sodium chloride forms out of its pure elements, the sodium gets oxidized as it loses an electron, and the chlorine gets reduced as it gains an electron. Logically, sodium is the oxidant and chlorine is the reductant. Of course not, that would make sense, it's the other way around. More accurately, redox reactions are reactions that change the oxidation numbers of elements, which are kind of like imaginary
I thought you said
charges.
Roblox
There's just
reactions.
a few rules you have to know to figure those out. Hydrogen is mostly +1. Oxygen is mostly -2. Halogens are mostly -1. Single elements are always 0, and the number of all atoms in a molecule always have to add up to the molecule's charge. So this would total
H2, what
0,
the
while
hell?
single ions
Hold
just have their
on,
charge as the
magnesium,
oxidation
2
number.
plus,
For example,
plus
in
11.
sulfuric acid, we have 4 oxygens, which
Hydrogen,
totals -8. We have 2
sulfur,
hydrogens, which brings the total
oxide.
to -6.
Oh my gosh,
Since
I'm
the
him.
whole molecule is neutral, sulfur must have an oxidation number of +6.
We do the math,
Just
it'd
by
be
looking at
equal
the
0.
oxidation numbers of reactants
This
and
is light
products,
work.
you can deduce the flow of electrons, which gives you
AG,
these
what the hell is
equations.
AG?
If redox
What's
reactions happen in
ZN?
acidic or basic solutions, you can balance out the charges with ions and fix the stoichiometry with water. Okay, now to this weird looking thing. I spared you from it because for describing electrons, this is very simple and this is not. But this is actually like pretty wrong. Electrons don't orbit in circles. Here's how it actually works. All electrons inside an atom are described by 4 quantum numbers: n, l, ml, and ms. N corresponds to the shells, so all electrons with the same n are in the same shell. Within the shells, we have
Holy
subshells
crap.
with multiple orbitals, which are 3-dimensional regions in space where electrons could be. We know these
In
exist thanks
space?
to Schrödinger's equation, which gives a probabilistic wave function. You can imagine it as a cloud, and the denser it is, the more likely an electron is to be there if we were to look for it. L describes the shape, and ML the orientation of orbitals in a subshell. There are 4 subshells called S, P, D, and F. If electrons have the same L, they're in the same subshell. If
Liquid?
electrons have the same N, L,
Neutral?
and ML, they're in the same
What's
orbital.
M?
Also, the number of orbitals increases
Miniature?
by 2 for every bigger subshell, starting at just 1 for S. The last quantum number describes an intrinsic property of electrons called spin, which can have 2
Spin.
values. Some guy named Pauli
Bro,
said 2
electrons
electrons
spin
can never have
now?
the exact same quantum numbers.
Bro,
inside
when the
one
hell
atom.
was this update?
Since MS can only have 2
I
values,
never heard
every
about this
orbital defined
update.
by N, L, and ML can hold a maximum of 2 electrons with opposite spin. Therefore, the S subshell can hold 2 electrons, the P subshell can hold 6.
Holy
D
frick,
can
are
hold
those supposed to
10,
be
and F
electrons?
can hold 14. Now, the
Why
quantum
they look
numbers
like that?
restrain each other like this, which means that the first shell can only have an S subshell, the second can have an S and a P subshell, and so on. This means that
so
the
on.
first shell can hold a total of 2 electrons, the second can hold 8, the third
8.
can hold 18, and generally
Okay.
the number of electrons a shell can hold follows the rule 2n squared, with n being the principal quantum number.
2n
The principal
squared.
quantum number, and therefore the total number of shells, increases from top to bottom in the periodic table from 1 to 7. Every
Holy
element has a
crap.
different number of electrons that fill up these orbitals, and the different subshells and orbitals are filled in a specific order called the Aufbau principle. Just write down the subshells like this and draw diagonal lines from top right to bottom left. To get an electron configuration, just look up the number of electrons of the element in the periodic table and fill up the subshells in this order until there are no electrons left. This would be the electron configuration of sodium. You can also look up the next smallest noble gas and shorten it by just referring to its electron configuration as the base, because those shells are full and don't change for any bigger elements. This is also how you can figure out the valence electrons for transition metals. Just look up their electron configuration, ignore the full shells of the next smallest noble gas, and the remaining electrons are the valence electrons. Easy peasy. Anyways, all this knowledge is going to cost you 1 subscribe and a thumbs up. Thank you very much. Your comment is my delight, and I shall now guide you find.
Holy crap, bro. Yo, you'll get a like. That was very educational. Alright, man. W video. I'm not gonna lie though, dude, that was exhausting. That was like, dude, that was the longest video I've seen in my whole life. Holy frick, that was so tiring. Oh my gosh. Chat, I'm gonna need a break real quick. I'm not gonna lie, that was holy crap. Dude, that was